Tem 23 participantes aqui.
Pronto, Flávio, eu te mandei o link agora da live. Tá
Ficando no YouTube.
Tá ativo.
Três participantes aqui.
Pronto, Flávio, eu te mandei o link agora da live. Tá
Ficando no YouTube.
Tá ativo.
Três participantes. Tem um delay absurdo no YouTube, né?
Uhum.
Ele tem um delay e também é bom se vocês estiverem logados aqui no Zoom, não deixar a página do YouTube aberta, porque pode ser que fique tendo um eco, sabe? Fica atrapalhando a comunicação.
Eu tirei o som do YouTube.
Ah, ok.
Aberto aqui só para ver. E aí, Eduardo?
Olá, pessoal, tudo bom? Flávio, Rodrigo.
Olá, professor. Bom?
Tudo bem.
Tem mais alguém aqui?
Bom, I have to shut down, tirar o som e o vídeo. Todo mundo, não é isso?
Uhum.
Ativar som. Ativar som. Como é que desativa o vídeo? Quando é que eu começo o
Acho que já pode começar.
Eu posso começar?
Por
Como é que eu
favor.
tiro o som, o vídeo de todo mundo?
Eu consigo tirar aqui. Pode deixar.
Hi. Good afternoon. I'm Flávio Garcia. I'm from CBPF, Brazilian Center of Research in Physics, here in Rio de Janeiro. And I'm here to host and present the speaker of this afternoon, or the speaker of this session of the conference. And the first speaker will be Elin Winkler. She's from CNEA. She's a researcher there at the CNEA and the CONICET, Instituto de Nanociências e Nanotecnologia, from Centro Atómico Bariloche, Instituto Balseiro, National University of Cuyo. She's an expert in magnetism and electrical properties of transition metal oxides and nanostructures. She's worked mainly with nanomagnetism, nanoparticles, and exchange bias. She will give a talk. She will talk about the name of his talk, his speech this afternoon will be about. Sorry about that. I don't have the program.
Okay. Thank you for the presentation. I will share the screen, right?
Yeah.
Can you see the screen?
Yeah.
Can you see well? Yes, and this, okay. Well, good afternoon, everybody. I'm very glad to participate in this symposium. Thank you to the organizers for the invitation. My name, well, as I said, Flavio is Elin Winkler. I work at the Atomic Center, which is located in a beautiful city of Bariloche in the south of Argentina. I will check the time, so yes. And today we're going to talk about how can we tailor the properties of magnetic nanoparticles by modifying, design, and fabricate different core shell nanoparticles. Let me change here because, yeah. If not, I can see the screen. Well, as a brief introduction, I would like to say that the nanoparticles are used in a wide range of applications that are going from the textile industry, going to environmental remediation, biomedical applications, energy, electronic devices, and in particular, by the core shell structure, this architecture allows to combine in a single nanoparticles two different materials. So in that way, we can combine two different functionality. For example, here, like in a cartoon, I drawing a magnetic nanoparticles, which is encapsulated with a material with optical properties. So we can use that for magnetic application and also for imaging. Also, when we fabricate core shell nanoparticle, could be that at the interface, the two materials are coupling, so the new material, the core shell nanoparticle, present different properties than the parent components. I have a problem with the, yes, one there. So in this talk, we're going to talk about different systems that we fabricate and how we tune the behavior. In particular, I'm going to mention 4 different applications. In the first one is more a basic study. We synthesize different systems in order to tune the magnetic anisotropy. And then we are going to apply this to different applications. One of them is a design of magnetoresistance devices. Another application is to design nanoparticles to improve magnetic hyperthermia. And finally, how can we design the functional nanoparticles with magnetic and catalytic activity? So we are going to start with the first point. The first point, how can we tune the magnetic anisotropy? Well, the magnetic anisotropy is one of the main characteristics that determine the range of application of particular systems. Here, for example, we are drawing as a function of the magnitude of the magnetic anisotropy constant, different applications. And for example, if the magnetic anisotropy is very low, we are talking about soft magnetic materials, and that can be used for transformer, and also biomedical applications require material with low anisotropy. And when we increase the anisotropy constant, we can design material for high density data storage, or in this range, we are talking about hard magnetic materials that can be used to design a permanent magnet. One way to characterize the properties of this system are through the hysteresis cycles. Yes, here we measure the magnetization of the system as a function of the magnetic field. And along the talk, we are going to talk about the hysteresis, the coercive field, which is proportional to the magnetic anisotropy in the case of nanoparticles. And this coercive field, we can synchronize it, and we can move from hard magnetic material to soft magnetic material. So remember that we are going to see several hysteresis cycles, and we are going to talk about the coercive field and the saturation magnetization. So what happens when we have a magnetic material? Below the transition temperature, for example, if we have a ferromagnetic material below the Curie temperature, the spins are oriented at order inside the material, but in order to load the magnetostatic energy, inside the material are formed different domains. Yes, in any this, here I drawing several like sketch domains. In each one of these domains, all the spins are oriented along one direction. And this corresponds to domain walls. Yes, the creation of a domain wall, it has an energetic cost. What happened for the application? All the time I require smaller and smaller dimensions, so we need to fabricate nanostructure material. But when we reduce the size of a material to nanometric scale, the system do not develop any more domain walls because it has an energetic cost. So the magnetic nanoparticles behave as a single domain, which means that inside the nanoparticles, all the spins are oriented, okay? And the nanoparticle present a huge magnetic moment that came from the contribution of all the spins in the nanoparticles. Now, along which direction that magnetic moment align? Well, in principle, the magnetic moment could be aligned along any direction if the material is isotropic, but usually the material presents some kind of anisotropy that could have different origins. For example, here could be a shape anisotropy that determines a specific direction, also a magnetocrystalline anisotropy due to the particular structure of the material. Also the stress could generate some specific direction. So these energies determine a preferential direction where the magnetic moments are aligned. So that anisotropy energy that as we mentioned, it has different origins. The anisotropy energy is proportional to the anisotropy constant and the volume of the nanoparticle. So if the application requests to reduce the size of the nanoparticles, this anisotropy will be reduced. And before of that, in this range, if we have this anisotropy energy, if we want to invert the magnetic moment of the nanoparticle, we apply a magnetic field in the opposite direction. So we want to move the magnetic moment nanoparticle in the opposite direction. When we perform the measurement, we measure the magnetization of the nanoparticle as a function of the coercive field. The hysteresis, the coercive field of this hysteresis loop will be proportional to the magnetic anisotropy and will be proportional over K over the magnetic saturation. So, as I said before, if we reduce the size of the nanoparticle, we are reducing the anisotropy energy that, again, remember that hold the magnetic moment aligned along one particular direction. So if we reduce the term, we'll arrive at a situation where the thermal energy will be larger than the magnetic anisotropy. So when we arrive to this situation, the magnetic moment will start to fluctuate, okay? And when we arrive to this situation, the magnetic moment will start to fluctuate along both orientation. So we are going to lose the information. For example, in this case, this material is not longer useful to high magnetic storage. Or, for example, if we want to design a magnet, well, we are going to lose that remanence. In this case, so the coercivity field is 0. Okay, so if we want to design a modern magnet, a permanent magnet, or if we want to design a material for high density data storage, where we want to the magnetization keep along one direction, because in that way we codify the information in a magnetic way, like each bit are related to one orientation of the magnetization, we need to increase the anisotropy energy. So one way to do that is to increase the volume, but we can do that because we want to reduce the size of the material. So the other way to do that is to increase the magnetic anisotropy. And how can we do that? Well, by fabricating core shell nanoparticles. Usually, the ferromagnetic material that has a very large saturation magnetization usually present small magnetic constant. On the contrary, the antiferromagnetic system usually has 0 magnetization or very small magnetization, and it has a very large magnetic anisotropy. So combining both materials, we can fabricate a system with larger anisotropy. So we're going to talk with a little more detail about that. In the case if we fabricate a core shell nanoparticle combining a ferromagnetic material with antiferromagnetic one, it happens if we look in detail at the interface, we could see that both phases are coupled at the interface. So if we want now to invert the magnetic moment of the nanoparticle, we have to apply a larger field to invert the magnetic moment, because the antiferromagnetic material has a larger anisotropy. So the coercivity field will grow up, and the value will be a proportional relation between the parameter of both components. But in this core shell system, we could find another situation. In the case of the coupling at the interface is not so strong, in that case, with which value we can compare that energy? Well, in that case, we compare the coupling energy, the exchange energy, with the anisotropy of the hard magnetic material, of the antiferromagnetic phase. So in this case, if this anisotropy is much larger than the coupling, in that case, we will invert the magnetization of the ferromagnetic one. Yes, the red spins in this case, we will invert that spins, but the ferromagnetic phase will remain unchanged. So in that case, we will see that we will find a preferential orientation when the magnetic field is along one direction. For example, in this case, the energy is down when at the interface, the spins at the antiferromagnetic and ferromagnetic are parallel. So if we want to invert, we have to exert an extra torque in the opposite direction to invert the ferromagnetic phase. So in this situation, how can we observe that exchange energy? Well, we observe an asymmetry in the hysteresis loop. We observe that the center of the hysteresis loop is shifted, and this field, that it's called exchange bias field, is proportional to the exchange interaction at the interface. So with all these ideas in mind, we're going to fabricate our systems. Well, our first challenge is we want to increase the magnetic anisotropy of the system. We want to fabricate a hard magnetic material, for example, for fabricate a new magnet. In that case, we choose a ferromagnetic material, the cobalt ferrite, that itself is it has a very large anisotropy, and we combine this cobalt ferrite with a cobalt monoxide. The cobalt monoxide is an antiferromagnetic material that has an order of magnitude larger magnetic anisotropy. So in this case, we grow up the antiferromagnetic phase, we synthesize nanoparticles of cobalt monoxide, and then we overgrow the cobalt ferrite over the cobalt monoxide. So if we expect that at the interface, it's establish the exchange gap. And to compare how the properties of our material improve, we also fabricate another core shell system where in this case, the core of the nanoparticles are the zinc oxide. The zinc, as you know, it has his last orbital, so its behavior is diamagnetic. So in this case, when the core of the nanoparticle is zinc oxide, the system won't present this exchange interaction. So we synthesize the system, first we synthesize the core, and then we use that as a seed to overgrow the shell. And here I show a core shell nanoparticle. Then we are going to see many more STEM images. In this case, as the mismatch between these two phases are large, the shell overgrow like small nanograins over the core. And this is a transmission electron microscopy images where the shell are the bright phases, the cobalt ferrite. This image is reconstructed with the electron diffraction that came from the diffraction rings of the cobalt ferrite. So the bright image corresponds to the cobalt ferrite. So here are the results. This hysteresis cycle corresponds to the zinc oxide encapsulated with the cobalt ferrite. Here, for example, it's very clear the core shell structure. Yes, and here the bright corresponds to the shell. And the coercive field is approximately 7 kilohertz. When we instead, when the zinc oxide core is the cobalt monoxide, the hysteresis cycle grow more than 3 times. Yes, the coercive field reach up to 3 Tesla. In this case, which is the difference between these two materials? Well, in this case, remember, the cobalt monoxide is an antiferromagnetic material, so the magnetic saturation will remain more or less the same, but this system presents exchange coupling at the interface, so the coercive field will result an average of the properties of both phases. So right now, when we synthesize the system, we think now how can we reduce the exchange coupling at the interface in order to move from the rigid coupling to the exchange bias regime. Well, and one way to do that, here, for example, represent, this is the antiferromagnetic material, and this is a ferromagnetic one, and this represents the exchange coupling at the interface. And one way to reduce the exchange coupling is to cut some of these bonds. And how can we do that? Well, replacing one of the magnetic ions, but by a non-magnetic one. And in that way, we are going to reduce this exchange interaction. And how can we do that? Well, by replacing the cobalt, which has a spin 3.5, by zinc, which has a 0 spin. So in that way, if we fabricate core shell nanoparticles where the core are always cobalt monoxide, but we systematically change the shell, replacing the cobalt by zinc, we can move systematically in that way, reducing the exchange interaction at the interface, the coupling at the interface, while the energy, the anisotropy energy of the antiferromagnetic phase remained constant. Well, we did that. We synthesized all the core, the cobalt oxide core, and we split that in 5 batches, and then we overgrow the shell over that zinc, the cobalt monoxide, yes, and we changed the shell composition. This one corresponds to the cobalt ferrite. It has a 25% of zinc. This has 50% of cobalt and zinc in that place, and so on, yes. When we do it in that way, we have the advantages that the system presents a very similar size. All the nanoparticle size are approximately 10 nanometers. As you can see, this is the histograms, the size histograms. And here you can observe some high resolution 10 images where you can observe the core shell structure. In some cases, you can observe the crystalline planes. So going to the magnetic result, in fact, we observe that when we systematically increase the concentration of zinc, the hysteresis, the coercive field, is systematically reduced, which is drawn here. And remember, in the previous system, we have a very large coercive field and 0 exchange bias. And when we replace a little of cobalt by zinc, suddenly we observe an asymmetry of the hysteresis cycle, and then it's systematically reduced. Why? Because we are going to reducing the exchange interaction at the interface. So how can we quantify a little more about that? Well, we have all the data to calculate the exchange interaction, which is proportional to that asymmetry of the hysteresis field, and we observe that this is systematically reduced when we increase the zinc fraction in the shell, and when we reduce the zinc fraction, is approach to the antiferromagnetic anisotropy. So, and if we move in that direction, we will change from the rigid coupling to the exchange bias regime. Moreover, from this value, we can calculate also the density of the exchange bonds. Why? Because in this system, when you fabricate a system and you make some calculation, you expect a very large exchange interaction, and usually the exchange bias field is 10 times more or less smaller than what you expected. And from this calculus, you obtain that result. That means that not all the spins at the interface are locked and induce this exchange interaction. So in that way, we could, by systematically change the shell stoichiometry of the core shell nanoparticle, we can systematically tune the coercive field, and we can also modulate the exchange bias coupling. So we are going to apply this to the next subject is how can we tune the tunnel magnetoresistance of the systems. Well, in a tunnel magnetoresistance, the tunnel magnetoresistance junction, for example, is formed by 2 ferromagnetic metallic thin layers that are separated by an insulator layer. So the tunnel electron conduction will be, it's found that the tunnel conduction will depend on the magnetic or the all the magnetic state of these three layers. I mean, the probability of tunnel conduction will be larger when both ferromagnetic layers are parallel, and will be smaller when the magnetic layers are antiparallel. So, in that way, if instead of talking about conduction, we talk about resistivity, we observe that when the both layers are parallel, the resistivity of the material is low, and when both layers are antiparallel, the resistivity is higher. So in that way, we can design devices with two resistivities, two resistance states that are, well, very, very wide. It's a lot of sorry, is used in many electronic applications, and for example, to read a field in magnetic memories. And in this case, to design a tunnel junction are requested, you have to make lithography, it's requested sputtering on white rooms. So there are also more simple systems that also the tunnel conduction, the magnetoresistance tunnel conduction are also observed. These, for example, are the granular films. In granular films that are composed by half metallic, the half metallic is a material where the conduction depends on the orientation of the electrons, and in this case, the tunnel barrier are composed by the intergrain between the half metallic material, okay? So what it is observed also again, that the system presents two resistance states. The resistance is lower when when you measure, this is the resistance as a function of the magnetic field. The resistance is low when the system is, the magnetization of the system is ordered, and is large in, when the system is disordered. Well, this maximum, it is found that is related with the coercivity field of the system. Also was observed tunnel magnetoresistance in devices formed by metallic nanoparticles. This corresponds, this image, for example, corresponds to the cobalt nanoparticles that are deposited, and it measures the conduction through these two electrodes. So again, the system presents two resistance states. A low resistance here, for example, is the magnetoresistance as a function of the field, and here are drawing the coercivity field. And again, the maximum of the magnetoresistance are related with the coercivity of the system, which means that at high field, when all the nanoparticles or the magnetization are ordered, the system presents a low resistance state, and at the coercivity field, when the system presents a disorder, the resistance of the system is larger. So now we think when we found previously, we can modulate in the coercive field in core shell nanoparticle, but systematically tune the shell of the nanoparticle. So we can fabricate devices where we can move the maximum of the magnetoresistance. So how can we do that? In this case, our plan was fabricate a magnetite, which is a half metallic compound. That means the conduction depends on the polarization of the spins, and we encapsulate the magnetite with a semiconductor with very large resistance. Yes. So then we deposit the nanoparticles and we measure the conduction through in this direction. So when we're going to one nanoparticle to another nanoparticle, the tunnel barrier will be composed by the shell of the nanoparticle. And again, what we expect? Well, we expect that when the blue line corresponds to a sketch of the coercivity, and the red line corresponds to the magnetic resistance. Again, when all the nanoparticles are oriented, we expect that the tunnel probability conduction will be the probability of the conduction will be larger, which means that the resistivity will be lower. And when the nanoparticles, when the system is disordered, the resistance of the system will be larger or the conductivity will be lower. So we fabricate the system with, again, we change the core, in this case is the magnetite, and we change systematically the shell. And then how we deposit the nanoparticles on different substrates. Well, we made this liquid air synthesis, where the nanoparticles are self-assembled, and then a very uniform layer are formed at the interface between the liquid and the air, and then we remove the liquid and the nanoparticles are gently deposited on the substrate. These are the substrate where we have the two gold electrodes that are here. This is a microscopy image. These are the gold, and here are deposited all the nanoparticles. They are this region with a large magnification, and we measure the conduction across this direction. So, and these are all our systems. Yes, these are the core shell system, and where here, remember, always the core is magnetite, and we change the shell. In this case, the shell is cobalt ferrite, and then we replace cobalt by zinc until we have zinc iron ferrite. Yes, and here you can observe some core shell structure. In this case, for example, you can observe the crystalline plane of the shell. Yes, and these one are dark field image. Well, in this case, I want to show that by this way, you can grow very uniform layer of several microns. Yes, this is more than 1 microns, and you can see all the nanoparticles. And you can observe that between the nanoparticles are a small gap that correspond to there we have a carbon, amorphous carbon that remains from the synthesis. And this, for example, are image of atomic force microscopy, where we measure a profile, and you can see that the width of the self-assembly is approximately 20 nanometers. And remember that the size of the nanoparticles are 10 nanometers. So this means that the layers are formed, but the self-assembly are formed by 2 layers of nanoparticles. And you can observe that here we have more than 1 micron, so there are many nanoparticles. The area is very, very large. I going fast from this slide, but you can observe that the coercive field, as expected, it's systematically reduced when we replace the cobalt by the zinc. So the coercive is result from an average of both of the parameter of both material. When we measure the current as a function of the voltage, we observe that this relationship is not linear, if not present this function that the voltage to the square 1 over V is proportional to voltage to the square. That is the expected one for tunnel conduction. And finally, we arrive to the magnetic resistance measurement that we observe also in maximum. This is correspond to the sample with 25% of zinc in the shell. And again, we observe 2 resistance states. The low resistance state, we measure high field, and a high resistance state. And the model for spin polarized intergrain tunnel, that was developed from single films formed by granular films. It says that the tunnel magnetoresistance is related to the square of the magnetization. This magnetization is what we obtain from the magnetic measurement that correspond to the blue one. This is the hysteresis cycle. If we made the square of the function and we normalize, we obtain this curve that is in very well agreement with the tunnel magnetoresistance measurements. So here we observe all the data. In fact, when the cobalt of the shell is replaced, we can systematically reduce the maximum of the magnetoresistance. So we can tune these two resistant states of the system. So the conclusion of the part is by the core shell system allowed to tuning the inversion fin of the tunnel magnetoresistance, and also we can tune the characteristic of the tunnel barrier, and these devices can be fabricated in a chemistry lab, which do not require very expensive equipment and clean rooms. So one thing that I have to be said that the value of the tunnel magnetoresistance is very slow, but you can fabricate the system in a very easy way in a lab. So you can test many different materials. And also a very important thing is that you can combine different functionality. Here we use a magnetic insulator, but you can use a ferroelectric or another material with different properties. So we can play with and design many different systems. So we are going to use all these things that we learned here to improve the properties of the material for magnetic hyperthermia. So we are going to biomedical applications. Well, as you know, in the magnetic hyperthermia, we are using magnetic nanoparticles. We apply, these nanoparticles are dispersed in a medium, and we apply an AC magnetic field. The nanoparticles so absorb magnetic energy from the AC magnetic field, and in a relaxation mechanism, that energy are dissipated to the medium that raise the temperature. So because in this way we can increase the temperature of the medium, it was proposed to cancer therapy. So the idea is you can inject the nanoparticles into a tumor. You can apply a magnetic field, which has an advantage is that AC magnetic field has a large penetration into the body, so you can produce a local heat into a body where, for example, a tumor is located. So in that way, if you increase the temperature to 42, 45 degrees, you can kill cancer cells. Or also, you can produce the apoptosis, that is a programmed death of the samples. So the method has several advantages, as it's a local therapy. It has a very small area of action. As I said, the application is remote because you can apply the magnetic field outside the body. Also sensitize the cells to apply later radiotherapy or chemotherapy. And also you can functionalize the nanoparticle with the specific molecules and to target specific cells. However, this method is only approved in a very few cases. It's approved in, for example, in Europe for a specific case of brain tumor. And in order to the method is widespread, we need to improve many things. Well, one of the things that have to be improved is the heating efficiency. It happened that because of the possible toxicity of the nanoparticles, the the agency that regulates the application of drugs require that the use of the nanoparticles, the concentration, requires that you can use very low concentration of nanoparticles. So the heating efficiency should be improved. And also it happened that when you made the experiment in the lab, frequently you observe that the nanoparticle induce a heating of the material, but then when you use or internalize the nanoparticle in the cells, the specific power absorption drops. So we need to fabricate the material that be independent of the viscosity. So with that idea, we propose to design a material. Well, as we said, we need nanoparticles that behave superparamagnetic at room temperature. That means that do not present remnants in order that the nanoparticles do not agglomerate and can be very well dispersed in a medium. This thin material, this is the behavior when you perform static measurements and with a very, when the characteristic time of the equipment is very large. And this material, when you apply and you measure, when you apply AC magnetic field, that in hyperthermia the frequency is very large, the frequency of that experiment is very large, so the characteristic time of the experiment is very, very low. In that case, the system presents hysteresis loss. And why is that? Because you have a magnetic moment of the nanoparticle, you apply an IC magnetic field, and there is a phase shift between the magnetic moment of the nanoparticle and the magnetic field. So this hysteresis loss, this area of this hysteresis cycle is proportional to the energy that is delivered to the medium. So, which is the mechanism where the magnetic nanoparticle relax? We have to understand that to improve the material. Well, there are two main relaxation mechanisms. One of them is the Brown relaxation mechanism, which is referred to when you apply a magnetic field, all the nanoparticles rotate in order to align the magnetic moment to the applied magnetic field, which means the magnetic moment is like attached to the magnetic nanoparticles. As the magnetic nanoparticles move into the medium, this relaxation time will depend on the viscosity of the medium. The other mechanism is the magnetic mechanism or the near relaxation mechanism. In this case, the nanoparticles are fixed in the space and only the spins of the nanoparticle, only the magnetization of the nanoparticle rotates. So in this case, as the magnetic nanoparticles are fixed in the space and only the magnetic moment will rotate, the relaxation time will depend on the magnetic parameter. So, and again, as in many phenomena in the physics, the real relaxation of the system will be the one with the shorter relaxation time. So, if the near relaxation presents a shorter relaxation time, the dominant mechanism will be the one, and on the contrary, if this one is this present smaller time, the dominant mechanism will be the Brown relaxation mechanism. And all, if they are similar, well, will be a mix of both. So, up to here, we learned that by core shell nanoparticles, we can tune the magnetic anisotropy of the system. So here we have a tool to tune or to move the near relaxation time and maintain, if the volume of the nanoparticle do not change, this relaxation, the Brown relaxation, will remain unchanged. So that was the idea of this work. And in fact, as the near relaxation is an exponential of the anisotropy, it will be very, very sensitive to the anisotropy. And again, we fabricate a magnetite and we encapsulate with cobalt ferrite. the cobalt ferrite has an anisotropy to 10 to 6, and we systematically replace the cobalt by zinc, and we reduce the anisotropy 2 orders of magnitude. In that way, we can change a lot this relaxation time compared to this one. Well, we did that. Here there are some 10 images. The core nanoparticle has 7.5 nanometers, and the core shell approximately 10 nanometers. And here you can observe the core shell structure. Well, here is just to show that all the nanoparticle systems present the same comparable size. And these are the magnetic properties similar to what we talked previously. In this case, by systematically change the stoichiometry of the shell, we tune the coercivity of the field, the coercivity field, and this is the magnetization as a function of the temperature, and we observe a change from superparamagnetic to Blockit regime, and this maximum is related with this energy barrier, and we can calculate the anisotropy that change an order of magnitude when we replace the cobalt systematically by zinc. So we arrive to the hyperthermia experiment. Remember, we disperse the nanoparticles in the medium. In this case, we disperse 0.5 nanoparticles in a solvent in example. This solvent has very low viscosity. And we measure with different frequency, with 200 kilohertz, 300, 500, 800, so on. And we measure the temperature of the medium as a function of the time. Here, for example, when the measurement is performed with 800 kilohertz, the cyst of some nanoparticles hits the medium 15 degrees in 40 seconds. So remember that for hyperthermia, we need to increase from 37 degrees, which is a body temperature, to 42. There are very few degrees. In this case, we increase from room temperature 15 degrees, okay? So there are a group of nanoparticles that produce a very large hyperthermia. But we observe that there are two groups of nanoparticles. There are three systems that produce hyperthermia, and there are other two that do not produce any heating of the medium. So, as the nanoparticles that produce a heating of the medium present a lot of cobalt in the shell, remember that the samples, the cobalt is the responsible of increase the magnetic anisotropy. So as these samples has a very large anisotropy, means that has a very large nil relaxation time. So these systems will relax by the Brown relaxation. On the contrary, as we reduce this parameter when we replace cobalt by zinc, we think that this system will be relaxed by the nil relaxation. So in this case, we have a change of relaxation mechanism. We can quantify the specific power absorption in this way. This is a conventional way to do that, where it is proportional to the specific heat and the heating temperature with the time. And we observe that the three samples, it has a very large specific power absorption. And on the contrary, when we replace the cobalt by zinc, the specific power absorption will be reduced. So how can we prove that these three samples, the heating of these samples are produced by the by the Brown relaxation time? So our idea, well, if these samples relaxed by Brown relaxation, if now we fix the nanoparticles, we are going to inhibit that kind of relaxation. And we did that. We disperse the nanoparticles in butter oil. The butter oil is solid at room temperature and present a viscosity 4 orders of magnitude larger. And when we did that, these 3 samples, the specific power absorption drop, present an important drop, which confirm that the relaxation mechanism of this system is the Brown relaxation mechanism. So up to here, we prove that by changing the shell composition, we can tune the Brown relaxation or the Neal relaxation. However, what we want to do is to be independent of the viscosity. We are not going, we didn't reach that either. So we have to make a step further to do that. To do that, it's very helpful, this kind of graph that was developed for Emilio de Bellasi and Enio Lima of our lab, that's drawing the relation between the relaxation time involved in the experiment. Here we have 3 important times. The Neal relaxation time that depends on the magnetic parameter that we know all these values. The Brown relaxation that depends on the viscosity and the volume of the nanoparticles. And this is the characteristic time of the hyperthermia experiment. This is the frequency of the AC field. So we just compare this time. And this graph help us to see if Brown relaxation is the dominant one, the smaller one, which is this zone of the graph, or the Neal relaxation is the dominant one. So we calculate that for our sample and we put it in this graph. So we have these 2 sets of points. The solid points correspond to the nanoparticles dispersed in exam. As we observe, these 3 samples that correspond to these 3, the samples rich in cobalt, present a relaxation by Brown. On the contrary, when we disperse the samples in butter oil, we shift toward the left of the graph because we increase the viscosity, so we increase this time and we move in this way. So in this case, the mechanism is mainly by Neal relaxation. So we understand this mechanism, but if we want to optimize the model, the linear model, it said that the optimum heating efficiency will be the case when the characteristic time of the experiment, 1 over the frequency of the AC field, this is 1 of the frequency of the AC field will be equal to the relaxation of the system. So this is the red line. So in this case, the 1 over the frequency of the system agree with the relaxation time of the systems. If by coincidence, these 3 samples are in the optimum condition. And remember, these 3 samples correspond to these 3 ones in the case that they are dispersed in exam. So here we have the answer. If we want that our nanoparticles produce a heating of the medium by the Neal relaxation, we have to tune the composition because this one, we have to tune a fine tuning of the composition around this red line. And we did that. We start to fabricate a sample here, a sample here, here, until we reach the maximum. And this corresponds to this image in that way, but systematically fabricate around this line, the red line, we obtain a maximum in the specific power absorption. And the active mechanism in this case is the Neal relaxation, yes? So, which is important here. In this way, by the core shell nanostructure, we can tune the Brown or Neal relaxation mechanism, and also we can adjust the Neal relaxation to optimize the magnetic hyperthermia in high viscosity media. Well, these results were chosen to illustrate the back cover of the nanoscale. And for that, we asked to an artist of Argentina, a very known artist, Pablo Bernasconi, and he lives in Bariloche. He made illustration for kids, and he made this drawing that represents nanoparticles made by clocks or part of watches that for us represent all the engineering that is necessary to do in order to synchronize the relaxation times of the nanoparticles. Well, and the last point, well, I don't have much time, but I will speak faster, is how we, this last point is related with the previous one, how we can tune magnetic nanoparticles with the catalytic activity of the magnetic nanoparticles. The motivation of this work was that in our lab, we work in magnetic hyperthermia since many years, and Maria Luz Mojica Picciotti, she made a PhD under the supervision of Roberto Sisler, and they internalized the nanoparticles into the cells. This is a cell, and the black spot correspond to nanoparticles, and then they apply AC magnetic fields. They made hyperthermia experiments. And what they observe is they measure before and after the hyperthermia. They heat the material with the massive field and look at, they didn't increase the temperature so much. They just arrived to 38 degrees. After the experiment, the cell didn't die. This is the measurement of the viabilidad celular. And after 6 hours, they observe that oops, I'm on time. Well, sorry.
I have only 5 minutes.
Okay, in 5 minutes, I will speak fast. Well, and here we arrive to the question if during the hyperthermia there are induced free radicals, and that are the reason why the cells are there. And the free radicals are very reactive molecules that has unpaired electrons, and in that way oxidize the molecular in the medium. And as in the cells, we have a peroxide that's decomposed into free radicals, and this is a very slow reaction, and it is known that the iron produce a catalytic reaction and produce a catalytic generation of these free radicals. And well, very recent work found that the nanoparticle produce a production of these free radicals. So we measure, I will pass this, I'm sorry, by electron paramagnetic resonance, we can measure these free radicals. And the way to do that is that with free radical, remember, is a very reactive molecules, and this technique uses spin trapping, that the radical is combined with the spin trapping, and in that way we can generate a small stable molecule, and we can measure, and we measure the interaction, the resonance of this electron, this unpaired electron, which interact with the surrounding. And each radical, each particular radical has a very different signal that is like a fingerprint of which radical we are talking about. At the intensity, the integral of this, the double integral of this signal is proportional to the concentration of this radical. So we measure different systems where we have, because in that case, we want to observe the role of iron 2 plus and iron 3 plus in the production of the free radicals. If this system has 1/3 of iron 2 plus, this, when oxidized, this nanoparticle has only iron 3 plus in the system, and then we have nickel 2 plus and manganese 2 plus and all iron 3 plus. And we measure, we fit the spectra. In that way, we can identify all the radicals that we have, and we can quantify that in each case. So here is the result, and I'm just finishing. We observe that the magnetite, we have iron 2+, present, here is the quantification. We use a pattern that we can know the number, the concentration of free radical. When we have iron 2+, the system presents a very large concentration of free radical. This is important that we have this large amount in pH 4.8. And when we change the pH, when we move to 7, we do not observe the generation of free radicals. And in the other cases, the production of free radicals drop. The oxidized nanoparticle also present a very low concentration. And this is the measure in the cell for the nanoparticles. When we hit the nanoparticles, the system presents a large concentration of free radicals. So we finish the result when in this way, the only message that I want that you keep is that when the nanoparticle presents iron 2+ in the surface, it has a very large concentration of radicals, and then when they are oxidized, their concentration of radicals drop. So in that way, we can tune if we want to produce a free radical, we produce a cell damage. We have to use a reduced surface. And if we can use that, in that case, for example, could be useful for if we use that nanoparticle cancer therapy. Or on the contrary, if we oxidize the surface of the nanoparticles are more safe, are more inert, and that can be used for magnetic resonance image, ophthalmological treatment, drug delivery. So to conclude, we designed several systems to tailor the magnetoresistance, the magnetic anisotropy, the hyperthermia, or the concentration of free radicals in the system. The people that participate, well, there are many people in our lab. This was made in strong collaboration with Enio Lima, that is a Brazilian researcher that lives in Argentina since many years ago, and also in collaboration with Roberto, Emilio, Marcelo. And also a large part of the work was made by Fernando Fabric, that was a postdoctoral student, also a Brazilian postdoctoral student that right now is in Campina, and also in collaboration with researchers of Spain, Italy, and this is the agency that support that the project. I'm sorry for the delay, and thank you very much for. Yes.
Very nice talk, very inspiring talk, mainly for the young research that is watching here right now.
Okay.
The time is a little bit tight now, and I think that we have time for few questions, only few questions. We have one question from Helena Rabelo Freitas. She wants to thank for the talk. I have a question about the core shell nanoparticle. Is it possible to fabricate the shells out of the organic materials? If so, do you know if the superparamagnetic effects will be affected positively or negatively?
Yes, well, we can change the coating of the nanoparticle. When we fabricate the nanoparticle by this method, is a result with oleic acid. And then, for example, when you have to internalize the nanoparticle into the cell, you change that with to another, you functionalize the nanoparticle, for example, with the strand or another molecule. And depend, for example, is very important because depending on this coating, the nanoparticles go to different parts of the cell. For example, it is known that when the nanoparticles are coating with the strand, that was the result that I showed, the nanoparticles are internalized in the lysosoma of the cells that present a pH very acid. So if you change the coating, the nanoparticles are located outside the cell, for example. So the answer is yes, you can change the coating. Also, there are many studies that they want to coating the nanoparticle with a specific molecule in order to even to attack some part of some cells. And well, it's a very large area to study. Related with the superparamagnetic result is the superparamagnetism is more related with the magnetic volume, that is the magnetic order part of the particles. So in principle, shouldn't be affected by the coating. What happens is, depending on the coating, sometimes the molecules are very large, so the interaction of the particles are lower. And if the coating is small, you have more interacting nanoparticles. And the interaction, the magnetic interaction, could change the change from superparamagnetic of blockage regime. So indirectly, I would say that could change the superparamagnetic behavior. Yes, the other volume, the nanoparticle plus the coating, we are going to talk about the hydrodynamic volume that's larger nanoparticles will influence the Brown relaxation mechanism, not the magnetic component of the. There are many things that are important in that question.
She has more two questions. Another question is the shell. Is the shell a type of coating method? Does it offers more stability to the nanoparticle? She wants to only know if there is the shell has promote any more stability to the system itself.
The question are here in the chat, right? So I didn't understand.
There's is in Q&A answer.
Yes, in the chat. The cobalt content.
Maybe it's better you listen her after the talk.
Okay. Okay. Well, I can.
There's one more question, Luciano Nascimento. He has a question. I don't know if can you read this question. Whether the cobalt content in the sample causes any distortion in the magnetic measurements of the hysteresis curve. What would be the method of obtaining this mass catalytic and supported for the use of the catalytic reaction of the methanol oxidation? What would be the method of obtaining this mass catalytic and supported for the use of catalytic reaction of methanol oxidation?
Okay, well, in the first question, the cobalt, in fact, because here said that it causes any distortion in the magnetic measurement of the hysteresis curve. Well, in fact, the cobalt is the responsible for increasing the magnetic anisotropy of the magnetic material. The cobalt in the ferrite, well, it's related with the spin-orbit interaction. When you want to increase the magnetic anisotropy of a particular material, we always think about cobalt because it has very strong spin-orbit interaction, and it's very difficult to move the magnetization. It has a preferential axis along the 1-1 axis, so it's very difficult to move the magnetization. And for that reason, it originates this enhancement of the magnetic anisotropy. So the answer is yes, is the responsible of the enlargement of the hysteresis curve.
Yes, there's no more sound. Yes, I think
Okay. Ah, yes, I have some. Yes, I say if I don't have any more time, I can answer the question by email. If you can write me, and I have no problem to answer.
I think it's better way now because they are really late now. It's my fault. Let's thank again speaker, and let's move on to another talk that will be given by Eduardo Granado. I'm sorry, I should.
Hi, Flavio. I can't open my camera, just the sound.
Yeah, I will open. It's I don't know how to do this, Eduardo.
It says you cannot start your video because the host has stopped it. So you have to go to participants, and in my name, you have to allow. Okay.
No, it's okay.
Yeah.
Thank you.
Yeah.
I would like to introduce Eduardo Granado. He's a professor in the UNICAMP University, and he will talk about sorry. We talk about quantum criticality in the layered iridate. Okay, you have 30 minutes, and I will sign you when 5 minutes is left. Okay.
Okay, Flavio. Okay. So I'd like to thank all the organizers for inviting me to be here. It's a great pleasure to have this opportunity to show some of our work here in our group at UNICAMP. So I'm going to share my screen. Let's see, screen, right? Share. Okay. So are you seeing my screen?
Yes, we can see.
Okay.
Presentation mode.
Yes. Okay, so I'll be talking about this. I decided to choose a specific work that we made related to quantum criticality in a layered iridate. So let me close my. See, okay, that should. So we should be seeing that. Okay, so this work was made in collaboration with a number of colleagues. Kaushik Samantha was a postdoc of mine. Danilo Rigitano and Italo Morales are PhD students, and Pascoal Pagliuso, my colleague, and Jean Souza is a student, a PhD student of Pascoal. This work was performed in TFGW UNICAMP. So I mentioned in the title about iridates, right? And I want to first to justify why we are interested in the iridates. So we have this vast range of options in the periodic table of elements to look for magnetic materials. You see the iridium is actually, it's part of this transition metal ions. So it's in the same column as cobalt and rhodium. But it's much heavier than cobalt, for example. So in principle, we should expect from the chemical point of view that iridium should be similar to cobalt, and by extension, in the first approximation, we should expect the iridium properties should somehow be related to cobalt properties. But it turns out that there is a catch here. Because when you go to the elements which are heavier in the periodic table, that changes a little bit the balance between the different energy interactions between that leads to the overall macroscopic behavior of the magnetism of the systems. So the reason is basically the interaction that is called a spin-orbit coupling, that most of you should know about it. So in principle, what we have is that this classical view of the electron around the nucleus. So if you have this, the electron going around the nucleus, basically we have an electric charge going around another electric charge. So it's pretty much like a current circuit. So if you have a current circuit, in principle, you expect to have magnetic fields being generated. And if you are in the electron point of view, so if you are an electron, you're actually seeing the nucleus going around you. And so you're seeing an electric charge going around another, around you. So that electric charge of the nucleus going around the electron, in the electron point of view, generates a magnetic field in the electron point of view. And so this magnetic field, in principle, may couple through dipolar coupling with any intrinsic magnetic moment that the electron has. So, and that's the spin, right? So if the electron has this spin magnetic moment, this spin magnetic moment of the electron should couple with the magnetic field generated by this this orbit of the nucleus around the electron, looking from the electron point of view. So, and that leads to the famous spin orbit coupling. That's the physical origin behind that. And it's important to, let me check, yeah. It's important to mention that this energy coupling becomes more important for ions which are heavier, basically because high atomic number. If you have a higher atomic number, first of all, you have more protons in the nuclei, so the charge of the nuclei is larger, and it generates a larger magnetic field. And not only that, but also for heavier elements, higher Z, it turns out that the electronic cloud tends to become closer to the nucleus because of Coulomb interaction. So, and because of that, it's pretty much like you have a circuit which is closer to the center, and so the magnetic fields that is sensed by the electron will be higher. So both effects together leads to a coupling with the Z, with the atomic number in the fourth power of the atomic number. So so when you go to heavier elements in the periodic table, you have higher Z, and the spin orbit coupling become more and more important. And you know, for high Z, it turns out that becomes a very important interaction when you need to consider the magnetic behavior of the system. So basically, that's attracted a lot of attention nowadays, because it's realized that actually this new interaction, not new, but this extra interaction that actually competes with other important magnetic interactions in the system may lead to new physics and many very interesting phenomena that were not actually noticed before. So that's why we are interested in this kind of system. So I'd like to show a little bit of how the electronic levels actually behave for the iridates. So as I mentioned, the iridates in the 5D family. So iridium 4+, which is actually the ion that we are most interested in this study here, has 5 electrons in the 5D shell. From these 5 electrons, we have this electric field. So if you have like a free ion, you have just all these levels, but then in a solid, you have the electric fields generated by the neighboring atoms, which are oxygen. And we are interested in an octahedral environment. So this 5D levels splits in the T2G level and the EG level. So it's a threefold orbital degenerated, and the EG is a twofold orbital degenerated because of the electric field. And so now, because we are talking about a heavy element, it turns out the next important interaction here is the spin orbit coupling. So in the spin orbit coupling, since we have like 5 electrons, and so we have you may have up to 6 electrons in the T2G. So we are most interested in this T2G level, And the spin-orbit coupling splits this T2G level in two different energies. First energy is JF equal 3/2, so it's a total angular momentum because of the spin-orbit coupling. The good quantum number here is the total total angular momentum, so which could be 3/2 or half, because T2G is an effective orbital moment of L equal 1, and so we have a spin half. So this sum of angular momentum may lead to two good quantum numbers, 3/2 or half, and there is a splitting, which is caused by the spin-orbit coupling. So now we have 5 electrons that occupy these levels. So JF equal 3/2 may have 4 electrons, because the Z component could be 3/2, half, minus half, and minus 3/2. So it may occupy up to 4 electrons. And then there is an extra electron that goes into this JF equal half level. But this, in principle, you may have two. You have 2 levels, but just 1 electron. And then you have this electron occupying this JF equal half. That turns out to be a very sharp electronic level, and because of electron-electron correlations, it leads to a gap opening due to these Coulomb interactions between electrons. So we have actually 2 levels, which is called LHB, which is lower Hubbard level, band or level, or upper Hubbard level. And so that's the basics of the electronic levels of these iridium 4+ iridates. If you look to more in terms of bands instead of atomic levels, which is actually the case. So instead of these discrete levels, we have like a band, which is a T2G band, like this. I will have this. Let me put that. So we have this T2G level in the atomic description, which in the solid description becomes a T2G band. And this T2G band splits in the JF equal 3/2, which is related to this level, this atomic level, and then this JF equal half, lower Hubbard band and upper Hubbard band, which are related to these levels, if you look just at the atomic levels. And then we have this occupied by 5 electrons, so that's what is mentioned here for the iridium 4+ ions, which are interested here. So that's the physics. So in principle, you may have an insulator that is first caused by the spin-orbit coupling, but it's also helped by, it's also influenced by this strong, or not strong, but average medium electronic correlations that happens in these JF equal half levels that actually splits the gap. So if you want to understand the magnetism of the system, you have to understand this physics, this basic physics of the electronic levels. So the material that you actually study is this one, strontium 2, iridium oxygen 4. So it has this crystal structure that I display here in the left. So in principle, we have the iridium in blue, which is surrounded by oxygen octahedra that I mentioned before, because it generates this octahedral crystal field of oxygens. And the strontium atoms are outside this network of iridium oxygen. So we have these layers A, B, C, and D, which are packed, which are packed in the C direction, and that's pretty much and also you have this tilt of the oxygen octahedra. So you may see here, for example, this oxygen atom here in the layer A is tilted. You see it from the left, but then in layer C, it has the same, the same glide with respect to layer A, but you see that the atom of oxygen is now tilted to the right. So you have like a tilting pattern between layer A and C, but you see that you have in between layers A and C, you have the layer B, which has a glide plane, which are actually displaced, which is slided with layer B are actually slided with respect to layer A. So that kind of defines the crystal structure of the iridates, which are actually very similar to the crystal structure of the cuprates, which are a very important system of materials in condensed matter physics, because it generates the high TC superconductivity. So one of the reasons why many people are interested in this kind of system is that you know, this level, that level scheme that I showed you in the previous slide is leads to one electron in a twofold degenerate level, which are splitted by correlation. So that's pretty much similar to the level scheme of the cuprates. So and there are predictions that these iridates also should show superconductivity because of the same physical ingredients of the cuprates. And there is a long story in that direction that I don't want to go in that way, because our results are something different, but that explains a lot of why so many people are looking at the iridates nowadays. So now if you look to the magnetic structure of this material, so I mentioned that you have these layers A, B, C, and D. Now if you look these layers from the top view, from the C-axis, now you see like squares. And these you see the iridium atoms, and then these arrows here represent the magnetic moments of the iridium. And you see that the magnetic structure is not a collinear magnetic structure. You see that since I mentioned before, you have this tilting pattern of the oxygen octahedra. This tilting pattern also leads to a rotation of the magnetic moments of iridium that kind of follows this tilting pattern of the oxygen octahedra. So you pretty much can you know think of this magnetic structure like a compass, where the magnetic moment is actually guided by the orientation of the oxygen octahedra. So if the oxygen octahedra is rotated to one side, the magnetic moment go to the same side, and then in the other, for the other iridium octahedra, if it's rotated in the other way, the moment also rotates the other way. And that's related to the very strong spin-orbit coupling, which actually leads to a very strong coupling between the orientation of the magnetic moments and the rotation of the octahedra. So I want to mention that these materials are, I mean, we are actually looking in this work to quantum critical behavior. What's a quantum critical transition, and how does it apply to this kind of system? So if I mentioned before that the system is insulating because of the gap opening caused by the spin orbit and the correlation effects. So we are interested to induce a metal insulator transition in this system, and first to perhaps induce the superconductivity, and second, perhaps look for new physics that may arise when the upper Hubbard band and lower upper Hubbard band touch each other. So, so that's from a basic physics point of view. Not much is known about what should happen. And in principle, you should be able to induce a metal insulator transition temperature. And if you have like a critical parameter like pressure or doping or some other critical parameter, and if you start with you know, a composition that you have like you are, you know, above a critical you know, sorry, if you have a tuning parameter which is you know, above a critical parameter, you may have an insulator phase. And so if this tuning parameter is reduced, this tuning parameter may lead to a metallic phase. And at this transition, at this point where have this critical behavior, new physics may arise. So you may look like you know, a temperature versus external parameter diagram. So if you have in the right side, you have the insulator behavior. In the left side, you have metallic behavior. But then when you have like this critical behavior, you have you know, a phase transition between this metal insulator phase. And this phase transition happens exactly at t equals 0. So, and that defines what you call a quantum phase transition. And it turns out when we have a quantum phase transition, there is some critical region that you have very strange behavior, and it's believed that even the superconductivity, it's in the high TC superconductors may be related with somehow with this, you know, with this strange behavior where interesting physics arise. So when you have a quantum phase transition, even though the quantum phase transition happens at 0 temperature, when you have the external parameter exactly at this transition, there is a very strange behavior that happens even at high temperatures, and that's why we're interested in these kind of materials. So first we try to, no, not only us, but many groups try to induce the metal insulated transition in the iridates by external pressure, but it turns out the resistivity of this material actually decreases with pressure as expected because the bands become broader, but then it doesn't go to metallic phase. It saturates in a still very highly insulating phase, and then after the pressure increases, the phase doesn't go metal. So in these iridates, it's not possible to induce, at least up to more than 100 GPa, it's not possible to induce a quantum phase transition by the application of external pressure. So now how you attack this problem? We propose a different path to reach this metal insulated transition. Now I have this diagram here again. This is a band diagram. We have the energy versus density of states. So this is pretty much the lower Hubbard band and upper Hubbard band, as I mentioned before. The LHB is fully occupied with electrons. The UHB is empty. So that's why you have an insulating material. And the Fermi energy, which is the energy of the last electron, the highest, the most energetic electron, is indicated here, the Fermi energy. So in principle, in the pure material, you have this gap of about a half electron volt. Now we want to make, instead of applying external pressure, we want to make a chemical substitution. So you may induce an impurity level. So inspired in semiconducting physics, you may have this acceptor level, which if you are lucky or if you're smart enough, this acceptor level could be very close to the Fermi energy. So for some substitutions, you may expect the acceptor level slightly above the Fermi energy. So that will lead to an insulating material because you don't actually close the gap. We just reduce the gap, like in a semiconductor, right? On the other hand, you may perform another substitution where the acceptor level falls behind the Fermi energy. So in that case, in principle, you are able to induce holes in the valence band, and because of that, you may have some levels in the valence band which are empty, and in this case, you may induce a metallic phase, and that's a way to go through a metal insulated transition. But if you are smart and lucky at the same time, you may have an acceptor level that matches exactly at the Fermi energy. And that gives a behavior which is neither metallic, neither insulating, is actually exactly at the quantum critical point. So, and then that's the point where you may have a quantum phase transition. And that's, with the not much time I have left, I want to convince you that's what we have in the material that we studied. So we come look again at the periodic table of elements. So if you look to the elements which are in the same table of iridium, which is rhodium and cobalt, so these are the elements which I mentioned before, it's chemically similar to the iridium. So that's where we may have a substitution that may induce an electronic level which are very close to the Fermi energy. So we try to perform rhodium or cobalt substitutions. Actually, rhodium substitutions were attempted before, and they induce a metallic phase. So it kind of overshoots the doping, and it's already known that the rhodium substitution leads to a metallic phase. So we try to do the cobalt substitution, and we studied that with some techniques. We studied that first. I mentioned before, you have this material, strontium 2, iridium, oxygen 4. And now we make this cobalt substitution. We replace 5% of iridium atoms, we replace by cobalt atoms. So we are hopeful that this substitution is still small enough not to disturb too much the crystal structure, but may change electronically the system. That's our hope. But first we checked what happens from the structural point of view. This is an X-ray diffraction profile around a pair of Bragg peaks, 116 and 200. SiO means strontium-2, iridium oxygen 4, pristine, without doping. SiCO means the cobalt doping. That's what we are really interested to check. We note that the Bragg peaks are not very much broadened by this cobalt substitution. The width of the Bragg, this is a synchrotron X-ray diffraction experiment. So the difference between the angles are just 0.5 between these two reflections, are just 0.5 degrees into theta. So the width is not large, neither for the pure sample, neither for the doped sample. So that gives us hope that the doping did not disturb too much the crystal structure. We actually note some asymmetry in the Bragg peaks. So you see here in the arrows that the Bragg peaks are asymmetrical for the doped sample and is symmetrical for the pure sample, and that actually indicates that actually indicates the presence of stocking faults in the crystal lattice. I won't get into too much detail into that, but this asymmetric Bragg peaks is a signature of stocking faults, means the following, means that this A, B, C, and D stocking, which is pretty much perfect for the pure compound when you have some 5% cobalt doping. We don't have such a perfect stacking of ABCD, ABCD, ABCD stacking. You may have stacking faults, which is generated by the disorder that the cobalt substitution induces in the structure. I mean, that unavoidably leads to some random component in the interatomic harmonic potential, and that's sufficient to disturb this ABCD stacking to something like AB, AB, CD, AB, CD, AB, AB, CD, some variation with respect to the stacking, which has some random component. That's the meaning of stacking faults. We performed a vibrational spectroscopy to check if the internal structural quality of the layers is preserved. So the Raman spectrum, the inelastic light scattering from these samples are very good quality. So the phonons that we show in the Raman spectrum are, pretty much the same width for the pure and for the doped compounds. That's a good news. For the cobalt doping, that's completely different with respect to other types of doping, like ruthenium doping in the system, that changes completely the Raman, the vibrational spectrum of the system. Here, in this case, it didn't change too much. So apparently, we can safely say that the cobalt substitution did not change the structure significantly. But then we go to the electronic properties. We have this resistivity as a function of temperature. For the pure compound, it's pretty much an insulating behavior. If you go to the cobalt doping, you see that the resistivity goes down a lot, but the material doesn't become metallic. It's still non-metallic, but it's not insulating anymore. That's pretty much what we expected to, or at least what I tried to convince that we are in the limiting case between one and the other. So we can fit this resistivity curve with a power law. So resistivity is a constant times temperature to minus a coefficient, minus x, and this coefficient is close to unity. And that's not the behavior that you expect for an insulating material. That's actually the behavior that you expected for a quantum phase transition. A quantum phase transition, we have this, you have this power law behavior of the resistivity. So then if you plot the conductivity, which is the inverse of the resistivity as a function of temperature in a log-log scale, that gives pretty much something very similar to the straight line, very close to a straight line, which is again a signature of power law behavior. And if you restrict ourselves to the low temperature behavior and fit the power law behavior just to the low temperature limit, we have this coefficient, which is very, very close to unity, x equal 1.00. So it's very close to unity. So it's not only a power law behavior, but the exponent is exactly 1. And that's very interesting. That's very unusual and very interesting. And because this number 1 is so, round, that suggests also a fundamental physics. So my time is pretty much up, so over. So I won't get into too much detail about that, except for some more detailed look of the electron phonon coupling, which again look for the Raman scattering behavior of the system. So now I look to the Raman scattering as a function of temperature, and if I look for a specific phonon, for the SICO sample, for the doped sample at low temperatures, you see that there is some asymmetric line shape. And that is telling me that I do have electronic, I again will not go through the full details of the, of the reasoning, but that leads to the conclusion that we have electronic excitations which are pretty much very low energy, and that's not expected for an insulating material. Insulating material, we have a gap of at least, let's say, half an electron volt or tenths of electron volts. What we see here, yes, my time is over. Yes, yeah. I know. Okay, I go to the conclusions. Just finishing the argument here. So we have these electronic excitations which are very low energy, like milli electron volt. And that suggests that although the material is not a metal, we have very low energy excitations. So, so now I go directly to the conclusions, and then we have a model for that. We can actually show that this very simple model where we have this lower Hilbert band and the impurity level exactly at the Fermi energy describes exactly the behavior that we have in both resistivity and Raman scattering. And that leads me to the conclusion that I'll just leave the slides for you to read. The most important one is that you have this quantum critical fluctuations that involves mixed character excitations, mixing charge, orbital, and magnetic. And I think we have new physics here that we want to study in more detail in the future. Okay, thank you very much.
Thank you, Eduardo, for the very nice talk. It's very, very interesting. Let me see if there's some question for you. We are open for questions. If someone has a question to Eduardo, just to make a sign here in the Zoom. There's no question. Actually, could you explain a little bit more about your model to explain?
Sure.
I don't know,
how much time do I have? All right. Yes, it's a very simple model actually. So we assume this. Huh? Say again?
Yeah.
So it's a very simple model. We have this lower Hubbard band, upper Hubbard band, and then you have a discrete level, which we assume is the cobalt-3 acceptor level. So we have this density of states, which we know that for those who already went through the solid state physics course, know that the density of states is proportional to the square root of the energy. The difference of energy with respect to the Fermi energy. So that's the behavior of the density of states of this band. From that, we know that what's the number of actually the number of holes that we may have in the valence band due to a thermal excitation of electrons from the valence band to the impurity level. Because if you have this thermal activation from the valence band to the impurity level, and that leaves holes in the valence band, which are thermally activated. So are not at zero temperature, but at a finite temperature, we have these holes. And by just statistical physics, you can actually calculate how many holes you have for each temperature. You know pretty much the average energy of each hole, right? Because statistical physics, you know that it's 3/2 of Boltzmann constant times temperature. And then you evoke a Drude model. Again, for those who studied solid state physics in the graduate course, you saw the Drude model. And then from the number of holes, you may estimate the conductivity. And just by doing the math here, you predict that the conductivity as a function of temperature should be linearly proportional to temperature. So that's exactly what we saw in our experiment. So that explains pretty much. And more importantly, we know the proportionality constant experimentally, and you know what should be theoretically with respect to the renormalized mass of the electrons. And we see that the renormalized mass of these electrons in the lower Hubbard band is about 700 times the free electron mass, which pretty much tells you that we have some physics which are very interesting, that resembles what another class of compounds that is of strong interest for our community, which are the heavy fermions. Heavy fermions are basically the materials with electrons that looks like they are very heavy, hundreds of times the mass of the free electron, or even thousands of times the mass of free electrons. Looks like you have a physics that calls for this heavy fermion physics in the system. So pretty much that's is calling for a new story for these materials. So we are connecting iridate physics, strong spin orbit coupling with heavy fermion materials.
Okay, thank you, Eduardo. Any more questions for Eduardo? There's no more question, actually. And Eduardo, thank you again for the very nice talk. And if someone there is any more question, further question to Eduardo, is just to send him a mail. And I think that now there is a break for until 16. To 4 p.m. actually, and the next section will start at 4 p.m. And thank you for all the speakers, and thank you for your attention. Bye.